So for extra practice for Chapter 5. Chapter 5 is, well, just a huge chapter. So I've got 28 randomized problems on here to try to help you guys focus on some different ideas, different ways we can solve some things, and different questions I can ask. I hope it helps. What is the molarity of chloride ions in a solution formed by mixing 50 ml of 0.1 molar magnesium chloride with 20 ml of 0.1 molar FeCl3? How many chloride ions are in the solution? As always, the first thing I like to do is write out the equation itself. So what I see here is I've got magnesium chloride, MgCl2, which I know is aqueous, and I got iron chloride, iron 3 chloride specifically, which I also know is aqueous. Now when I mix these two things together, we're actually going to have no reaction. They're both completely soluble. They're both with chloride, so nothing's going to crash out. It's not a precipitation reaction. But that's okay, because what I want to know is the molarity of chloride ions in solution that's formed by mixing these things together. So let's see what we've got. We've got 0.100 molar magnesium chloride, and we've got 50 milliliters of that, which is 0.0500 liters. And we have a 0.150 molar solution of iron 3 chloride, and we have 20 milliliters of that, which is 0.0200 liters. So first thing I'm going to do is I'm going to figure out how many chloride ions I have in each piece. Then I'm going to add those back together, figure out their overall molarity. For magnesium chloride, remember you can take your molarity times your volume to figure out the number of moles you have. If we have number of moles, we can use Avogadro's number to find out number of ions. So I've got 0.100 moles of magnesium chloride for every 1 liter. That's what this is telling me. I like to write it out in moles per liter because it helps me see the conversion factor better. I have 0.0500 liters of this, which cancels out my liters. Now I'm in moles of magnesium chloride. So now I'm going to convert to moles of chloride. I have 2 moles of chloride ions for every 1 mole of magnesium chloride. This cancels out moles of magnesium chloride. I've now got moles of chloride ions. Now I can use Avogadro's number. And I find when I multiply this out, I get 6.02 times 10 to the 21st chloride ions. I'm going to do the same thing with my iron 3 chloride. I've got a 0.150 molar solution, so 0.150 moles of iron 3 chloride per 1 liter of solution. And I have 20 milliliters of that, so 0.0200 liters. I've got 3 moles of chloride ions for every 1 mole of iron 3 chloride. And now I can use Avogadro's number, 6.022 times 10 to the 23rd chloride ions for every 1 mole of chloride ions. And that gives me 5.42 times 10 to the 21st chloride ions. Now I figured out how many chloride ions are in each system. I want to figure out my overall. Now that I've determined how many chloride ions I have in each solution, I can go ahead and answer the overall question. What is the molarity of the chloride ions in the solution? Excuse me. I haven't actually calculated this yet because I forgot that the question asked for this. I just figured out how many chloride ions I had. But how can I go about this? What I'm going to do is I'm going to add up how many chloride ions I have in total. So 6.02 times 10 to the 21st chloride ions from my magnesium chloride solution. Excuse me, my allergies are killing me. plus 5.42 times 10 to the 21st chloride ions. And I find this to be 1.14 times 10 to the 22nd chloride ions. I want molarity. Molarity is moles per liter. So I need this in moles. And this is where I didn't even think to calculate. So 1.14 times 10 to the 22nd chloride ions. I need to convert that to moles of chloride. I'm going to have to multiply this. So 1 mole of chloride ions divided by Avogadro's number, 6.022 times 10 to the 23rd, which should be a 3. So 1.14 times 10 to the 22nd divided by 6.022 times 10 to the 23rd gives me 0.0189 chloride ions, moles of chloride ions. I want that in concentration though, so I want that in molarity. I'm going to take that 0.0189 moles of chloride ions and divide it by the volume of my total solution in liters. I have 50 mils and 20 mils, 70 mils total, which is 0.0700 liters. And I find this to be 0.270 molar in chloride ions. Now, why do I care what my molarity of my chloride ions is? Well, I could use this to say react this with a silver chloride solution and figure out how much, or a silver nitrate solution rather, and see how much silver chloride could crash out. I could do all kinds of things with this. Sometimes, remember, chloride is usually soluble, but we do have some exceptions to solubility with chloride. So I could take these two solutions, mix them in with something else that's going to form an insoluble chloride compound, and using this information, figure out how much of a different product I could isolate. Okay. What happens when aqueous solutions of barium nitrate and potassium sulfate are mixed? Well, let's think about this. We've got barium nitrate and potassium sulfate. Barium nitrate, soluble. Potassium sulfate, soluble. We're going to swap ionic partners here. So I've got barium 2 plus, and I've got NO3 minus. I've got K plus, and I've got SO4 2 minus. The barium's going to go with the sulfate. Potassium and nitrate will be together. Potassium nitrate is soluble, so that will be aqueous. Barium sulfate is insoluble. That will form a solid. So this is called my molecular equation. If I wanted to write out my net ionic, I know I'm forming barium sulfate. Barium 2 plus and sulfate 2 minus. And my spectator ions are potassium and nitrate. Specifically 2 moles of potassium, 2 moles of nitrate, but just the ions themselves, potassium and nitrate ions, are spectators. What about if I mix aqueous solutions of sodium chloride and potassium carbonate? Sodium chloride is aqueous. Potassium carbonate, K2Cl3, is also aqueous. I'm going to swap partners here. So sodium's going to go with carbonate. Potassium's going to go with chloride. Potassium chloride is aqueous. Sodium carbonate is also aqueous. So instead of writing it like this, because they are both in fact aqueous, we write no reaction. We swapped partners, nothing happened. The reason is, and if you need to write any of this down, pause the video, but the reason is what actually exists in solution here. We started out with a solution of sodium chloride in one containment. So sodium ions floating around, chloride ions floating around. We added this to a mixture of potassium carbonate. When we mix these together, we're going to have sodium ions floating around, chloride ions floating around, potassium ions floating around, and carbonate ions floating around. None of them care. None of them are going to form any sort of precipitate. So we call this a no reaction because nothing forms. So your solubility rules can tell you what's forming or sometimes that nothing's forming. What happens when aqueous solutions of ammonium carbonate and silver acetate are mixed? Ammonium carbonate, NH4 is ammonium, NH4 plus specifically is ammonium. Carbonate is CO3 2-. So this will be NH4 2 CO3. Silver acetate, silver Ag plus, acetate CO3 or CH3 COO3-. So AgCH3COO. My molecular equation I've got NH4 2 CO3. This is aqueous, reacting with AgCH3COO, which is also aqueous. I'm going to swap partners here. The ammonium is going to go with the acetate, silver with the carbonate. It's going to give me ammonium acetate, which is aqueous, and silver carbonate, which is insoluble. So my ionic equation here, my net ionic, equation will have CO3 2-, aqueous, reacting with 2 moles of silver, ions, which are aqueous. Ions are aqueous by definition, that's how they can exist, forming 1 mole of silver carbonate, solid. My spectator ions are my NH4 plus and my CH3 COO minus. Definitely forgot the letter C in here. What about if we mix aqueous solutions of copper 2 sulfate and ammonium sulfide? So copper 2 sulfate, CuSO4, that is aqueous. Ammonium sulfide, NH4, 2S. Sulfide is just S2-. That is also aqueous. Swap your ionic partners. So copper sulfide and ammonium sulfate. Copper sulfide is insoluble. Ammonium sulfate is soluble. So again, this is my molecular equation. my net ionic would be my copper 2 plus ion plus my sulfide ion, giving me copper 2 sulfide, which is solid. My spectators are my sulfate and ammonium. Okay, number 6. When 1.25 liters of a 0.05 molar lead 2 nitrate solution and 2 liters of 0.205 molar sodium sulfate solution are mixed, calculate the mass of the precipitate that is formed. So I've got lead 2 nitrate, which is aqueous, reacting with sodium sulfate, which is also aqueous. Swap partners. I'm going to form lead 2 sulfide and sodium nitrate. Now, first, you should know your solubility rules. But even if you sometimes get mixed up, this is telling me a precipitate is forming, so one of these has to be insoluble. Group 1 metals and nitrates always soluble. Therefore, although you should remember that lead 2 sulfite is insoluble, this kind of helps remind you as well. Not quite done. Balance out your equation. 1 lead, 2 nitrate, 2 nitrate, 2 sulfate, or 2 sodium, 1 sulfate, 1 sulfate. So we are now balanced as well. It may not matter in the calculation we're doing, but it's always good practice to balance just in case. Then write down what you've got. You've got 0.0500 molar lead 2 nitrate, and you got 1.25 liters of it. And you have a 0.0250 molar solution of sodium sulfate and 2 liters of that. So I have volumes and concentrations of both species. This is a limiting reactant problem. There are a couple ways you can do limiting reactant. I'm going to do a different one right now just to get you guys comfortable with the different methods. So I've done them different ways in the videos for the lecture, different ways in the notes, etc. because I want you guys to find the path that's more comfortable for you. Excuse me. So in this one, I'm going to do Dr. Fry's method, and I want to ask how many mils of sodium sulfate do I need, or how many liters, this is all in liters, of sodium sulfate do I need to completely react all of my lead 2 nitrate. I find this path to be the easiest way, even though this is only going to tell me right away what my limiting and access reactant is. Doing it this way, reacting one to use up all of the other and seeing if you have enough, is the easiest way to identify the limiting reactant, the access reactant, how much access is left over, and then do the second calculation to figure out how much product you're actually going to make. So number of liters of Na2SO4 is what I'm trying to solve for. I know I have 0.0500 molar solution of lead 2 nitrate, which is the same as 0.0500 moles of PbNO3 to 1 liter of PbNO3 solution. And I have 1.25 liters of that solution. This step right here has canceled out my liters, and now I have moles of lead 2 nitrate. Now I can use my balanced equation to calculate how many moles of sodium sulfate do I need. I need moles so I can eventually use the concentration to get to liters. So I see that 1 mole of sodium sulfate reacts with 1 mole of lead 2 nitrate. This cancels out my moles of lead 2 nitrate and gets me to moles of sodium sulfate. And now I'm going to use that molarity to figure out the number of liters I need of sodium sulfate. So I have a 0.02500 molar solution. Remember, that means 0.0250 moles per 1 liter, which means I can write it either direction. So I'm going to say 1 liter of sodium sulfate solution to 0.0250 moles of sodium sulfate. This gives me 2.50 liters of Na2SO4. What does this mean, though? This specifically, it's not an answer yet. I'm not to the answer to the question. But what this means that if I want to react all of my lead 2 nitrate, every bit of it I have, I would need 2.5 liters of sodium sulfate. I don't have enough. Do I have enough? Na2SO4? No, I don't. That means sodium sulfate is my limiting reactant. So that means I'm going to use sodium sulfate to figure out how much of my lead 2 sulfate I can actually make, because this is the species that's going to limit how much I could actually make. So number of grams, PbSO4, when it says mass, it means grams, that I can make. I'm starting off with a 0.0250 molar solution, so 0.025 moles of Na2SO4 to 1 liter of solution. I have 2 liters of that solution, so that's where the 2 comes in. It doesn't come in this conversion factor stays whole. The 2 comes in beyond that. This cancels out my liters of solution. Now I've got moles of sodium sulfate. I know I have 1 mole of lead 2 sulfate for every 1 mole of sodium sulfate. Now I've got moles of lead 2 sulfate. I can add up the molar mass of that. It's 303.3 grams of lead 2 sulfate per 1 mole of lead 2 sulfate. And this gives me 15.2 grams of lead 2 sulfate. That is my answer. So if I mixed 1.25 liters of a 0.05 molar solution of lead 2 nitrate with 2 liters of a 0.025 molar solution of sodium sulfate, I would isolate 15.2 grams of lead 2 sulfate. Doesn't seem like very much. Seems like a pretty small amount of the solid coming out, but these are pretty weak concentrations here. So I'm not too surprised that it's so weak, or such a small amount. Number 7, how many liters of a 0.1 molar HCl solution are required to completely react with 13 grams of magnesium carbonate in the following reaction? So I've got 13.0 grams, 0.100 molar, it's 0.100 moles per 1 liter of solution, and I want to know my number of liters to completely react all of my magnesium carbonate. So number of liters of HCl, I'm trying to completely react 13 grams of magnesium carbonate. Convert that to moles of magnesium carbonate. Add up the molar mass, and you should find the molar mass to be 84.32 grams per mole. The equation is balanced. You should always check that, but the equation is balanced, which makes my life easier. we've got 2 moles of HCl for every 1 mole of magnesium carbonate. I know I have 1 liter of HCl solution for every 0.1 moles of HCl. So that's canceled out my grams of magnesium carbonate, my moles of magnesium carbonate, my moles of HCl, and left me in liters of HCl. The answer is 3.08 liters of HCl solution. So again, kind of seems like a large number, but 0.1 molar is a pretty weak concentration, so it's just going to take more of it. 0.1 molar doesn't have a lot of moles of HCl in it. The following reaction occurs in aqueous solution. Complete and balance the molecular equation and net ionic equation. So I've got potassium sulfite, and sulfuric acid. When this reacts, I'm going to form swap ionic partners here. So K2SO4, which is aqueous, and H2SO3, which is also aqueous, but will decompose. Remember, this is one of your gas reactions. So this will actually form K2SO4, but the H2SO3 will break down into H2O and SO2 gas, which will be released. So the molecular equation here, K2SO3 plus H2SO4 will give me K2SO4 plus H2O plus SO2 gas, and H2O is a liquid. Net ionic, I've got SO3, 2 minus, reacting with 2 moles of H plus, giving me H2O, liquid, plus SO2 gas. These ones get confusing for students, so please make sure to be aware that this is going to happen. You've got these 3 that can break down. You've got H2CO3 that goes to water and CO2, which is released to air. You've got the H2SO3, and then you've got an H4OH, which gives you H2O and ammonia. So please make sure and be aware of these and watch for these coming about. Okay. Calculate the mass of solid sodium chloride that must be added to 1.5 liters of a 0.1 molar silver nitrate solution to precipitate all of the silver ions in the form of silver chloride. So I've got NaCl, which is aqueous. I'm adding this to a silver nitrate solution, which is also aqueous. Swap ionic partners, forming sodium nitrate, which is aqueous, and silver chloride, which is a solid. I know I have 0.1 molar silver nitrate, and I have 1.50 liters of it. And I want to know the mass of sodium chloride needed to precipitate all of that out as silver chloride. So number of grams of NaCl I have a 0.1 molar solution, which is 0.1 moles of silver nitrate, to 1 liter of silver nitrate solution. I have 1.50 liters of silver nitrate solution. Now I'm in moles of silver nitrate. I can use my balanced equation to get to moles of sodium chloride. It's 1-to-1 ratio, but you should still write this out. Cancels out my moles of silver nitrate, gives me moles of sodium chloride. Add up the molar mass, sodium chloride, 58.44 grams of sodium chloride per 1 mole of sodium chloride. Gives me 8.77 grams of sodium chloride. So if I wanted to precipitate out all of my silver as silver nitrate from this solution, I would need to add 8.77 grams of sodium chloride to that solution. So basically you've got this floating around in solution, and you're gonna form your solid, which you see here. Determine the oxidation number of the red element in each of the following compounds. So remember, oxygen, always -2. There's 4 of them overall, so I'd get a -8 charge here. When you get something like H2PO4, this can actually split up in, you can say PO4 3- if you would like, and 2H plus, and then do it that way. Otherwise, recognize here that that hydrogen will be +1, so overall +2 charge. If you did it as PO4 3-, I'll talk about that in just a sec. But the hydrogens are each +1, so overall +2. Oxygens are each -2, overall -8. We do have a negative charge here. This is giving me +2, -8. Overall, it's a -6. I need a -1 charge, so phosphorus must be +5. The other way to do that is to recognize H2PO4- would be 2H plus a PO4 3-. Each oxygen is -2, so an overall -8 here. I need a -3 charge overall, so phosphate must be +5. So phosphate here has a +5 oxidation state, which means that it has to be B, C, or D. What about SO3 2-? Oxygen, -2 charge, overall -6. I need a 2- overall charge for the entire ion here, which means sulfur must be +4, which means B is out. N2O4, each oxygen is -2, so -8 overall, which means I need a +8 overall because it's a neutral compound, which means each nitrogen must be +4. C must be our answer. Remember, oxidation numbers come back in second semester, so you can't just learn them now and forget them. You will need them again. Sulfuric acid dissolves aluminum metal. Suppose you wanted to dissolve an aluminum block with a mass of 23.4 grams. What volume of 18.4 molar H2SO4 would you need? Well, you've got aluminum metal, which is going to be a solid, reacting with sulfuric acid, H2SO4, which is aqueous. This is a single displacement reaction. Al2, SO4 is aqueous, and it also produces H2 gas. Balance this reaction out. I'm going to have a 2 here, a 3 here, and a 3 here. I have an aluminum block that has a mass of 23.4 grams. I want to know if I have 18.4 molar H2SO4, what volume will I need here? Most often we mean volume in milliliters. Unless we say liters, we mean milliliters. So I want to know the number of milliliters I need of H2SO4. if I'm trying to dissolve a 23.4 gram block of aluminum metal. Convert that to moles of aluminum. Aluminum's atomic weight is 26.98 grams, so 1 mole of aluminum weighs 26.98 grams. Now that I'm in moles of aluminum, I can use my balanced equation to convert to moles of sulfuric acid. I see I need 3 moles of sulfuric acid for every 2 moles of aluminum reacted. Now that I have moles of sulfuric, I can go ahead and use my molarity here, 18.4 molar, where that means 18.4 moles of sulfuric acid to 1 liter of solution. So 1 liter of H2SO4 solution to 18.4 moles of H2SO4. Now I'm in liters of solution. I can easily convert to milliliters. 1,000 milliliters of sulfuric acid to 1 liter of sulfuric acid. The answer is 70.7 milliliters. But what does that mean? It means it would take 70.7 milliliters of an 18.4 molar solution of sulfuric acid to dissolve a 23.4 gram aluminum block. Why did I give you density? It's just useless information. Sometimes that's what happens in experimentation, and you guys have to be able to decide if the information is useful or not. So number 12, how many grams of silver chloride can be formed when 25 mils of a 1 molar silver nitrate solution is mixed with 30 mils of 0.75 molar magnesium chloride? So let's write out our balanced reaction. First, I've got silver nitrate, AgNO3, and this is aqueous, reacting with magnesium chloride, MgCl2, also aqueous, and I'm told I'm forming silver chloride, but either way, let's look at our swapping our partners. There's my silver chloride, and I'm also going to form magnesium nitrate. Silver chloride will be solid, it is insoluble, and magnesium nitrate, MgNO3 is soluble. Let's go ahead and balance our equation. I need 2 nitrates, 2 silvers, and that gives me 2 chlorides as well. So now my reaction is balanced. It's amazing to me how much I can put on the large eraser by accident, but never back to the pen. Okay, so again, you don't have to, but I like to do is write down what I know I'm starting with. I'm starting with 1 molar silver nitrate, and specifically 25 milliliters of it, which is 0.0250 liters. For magnesium chloride, I'm starting out with a 0.75 molar solution and 30 mils of that, so 0.0300 liters. Because I am given volumes and concentrations for both reactants, this is a limiting reactant example. And I'm going to solve it the way through our condensed but 6-step method, just because if you guys can learn that way and learn it well, you guys will have a better chance being able to calculate excess reactant remaining at the end of a calculation better. And I think going into the exam, that's a good practice. So let's see, how many mils? When I say mils, I mean milliliters of magnesium chloride are needed to react all of my silver nitrate. Now, I've been asked by students, how do I know which one to pick? How do I solve for magnesium chloride and start with aluminum nitrate or silver nitrate? Truthfully, I don't. I just pick one and solve for the other. It's just completely random. So for this one, I'm going to say number of milliliters, magnesium chloride, MgCl2. If I react all of this silver nitrate away. How many mils of magnesium chloride, my 0.75 molar solution, will that take? I have 1 molar silver nitrate, which is the same as 1.00 moles of silver nitrate in a 1 liter solution. I'm going to multiply that by the volume of solution I have, which is 25 mils or 0.0250 liters. And that cancels out my liters of silver nitrate, and now I have moles of silver nitrate. Now that I have moles of silver nitrate, I can use my balanced equation to calculate over 2 moles of magnesium chloride. I see it takes 1 mole of magnesium chloride to react 2 moles of silver nitrate. That's from my balanced equation. That's canceled out my moles of silver nitrate. I now have moles of magnesium chloride. Now I'm going to use my molarity of magnesium chloride. Remember, that means that's 0.750 moles of magnesium chloride per 1 liter of magnesium chloride solution. And I can flip that either direction. I'm going to put 0.750 moles of magnesium chloride on my denominator, specifically because I need them to cancel out. That's how I know it needs to go in the denominator. And I'm going to put 1 liter of magnesium chloride in my numerator because I'm trying to solve for milliliters of solution. This gives me liters of solution. 1,000 mils of my magnesium chloride solution equals 1 liter of my magnesium chloride solution. That cancels out my liters of solution and gives me milliliters. And I see this answer here is 16.7 mils of magnesium chloride. Now, what does that mean? What that means, it's not my answer. It's not my answer at all. I'm highlighting it for a sec so we can talk about what it means. What it means is it would take 16.7 milliliters to react all of the silver in this sample and precipitate it out as silver chloride. That's what it means. It means I need 16.7 milliliters of it, of this specific, or this specific, whichever you want to look at it, more magnesium chloride solution. Do I have enough? Yeah, I have 30 mils of it. I have more than enough. So if I was to ask you how much access do you have, at the end of the reaction, you could say 30 mils minus 16.7 mils, and your answer here would be the amount of access you have in milliliters. But that's not what we're asking for in this question. That is what it's telling me, though. With this, it's also telling me that the silver nitrate is my limiting reactant. And magnesium chloride is my access reactant. So with that information, I'm going to use the limiting reactant to see how much silver chloride could I make based on these reaction conditions, because this is what I'm actually trying to solve for. So number of grams of silver chloride. I know it's going to be limited by my silver nitrate. The silver from my silver nitrate is going to run out first. Got 1 molar silver nitrate, so 1 mole of silver nitrate per 1 liter of silver nitrate solution times 0.0250 liters of silver nitrate solution Now I've got moles of silver nitrate. I can convert that into moles of silver chloride. I know 2 moles of silver chloride are produced for every 2 moles of silver nitrate consumed. I've got moles of silver chloride. Now I can convert to grams of silver chloride. I know there's 143.35 grams of silver chloride to every 1 mole of silver chloride. And when I calculate this out, this cancels out my moles of silver chloride. When I calculate this out, I find my answer to be 3.58 grams of silver chloride. So all of this math, all of this giant mess, all of this page means if I combine these things together, I should get 3.58 grams of this sample out. So again, if you wanted to picture this, how it's actually working, you've got a solution with silver ions and nitrate ions. You've got a second solution with magnesium ion and chloride ions. And you're going to combine these two together. When you combine these together, you've got these silver ions in solution. You've got these nitrates in solution. You've got magnesium 2+ in solution. And you've got chloride ions in solution. The silver finds a chloride and precipitates out. The silver finds a chloride and precipitates out. The nitrate is acting as a spectator ion, and the magnesium chloride is in excess. So all the silver is going to run out. Sorry, my cat only decides to act crazy when I'm actually making a video, apparently. But the magnesium, so all of the silver is going to disappear. There's still going to be some chloride ions floating around, though, because that's part of my excess reactant. Okay, how many grams of glucose C6H12O6, which has a molar mass of 180.2 grams per mole, are present in a 365 milliliter solution that has a 0.488 molar concentration? So I'm trying to find number of grams of glucose, C6H12O6. I know I have a 0.488 molar solution, which is 0.488 moles of C6H12O6 per 1 liter of solution. And I have 365 milliliters, which is 0.365 liters of that solution. This step right here just gets me back to moles of glucose. I have moles of glucose. I have molar mass. I can easily find grams. So times 180.2 grams of glucose per 1 mole of glucose. This cancels out my moles of glucose and gives me grams of glucose. And I find the answer here to be 32.1 grams of C6H12O6. Again, we need to convert this to liters. But this also means that, say I need to prepare 365 mils of a 0.488 molar solution of glucose, I would dissolve 332, I keep saying 300 because of that value, I'm sorry. I would dissolve 32.1 grams of glucose in water, and then I would, so let me just draw this out. You've got a very sad looking Erlenmeyer flask here. I would add to this 32.1 grams of glucose. And then I would add enough water so the total volume is 365 milliliters. What volume of a 0.15 molar KCl solution is required to completely react with 0.15 liters of a 0.175 molar lead 2 nitrate solution in this reaction? So I've got 0.150 molar, and I want to know volume, which unless otherwise specified, give me milliliters, please. I've got lead 2 nitrate, and I have 0.175 molar, and I have 0.150 liters of it. I want to know the milliliters of KCl. So I've got 0.175 moles of lead 2 nitrate. In 1 liter of solution. I have 0.150 liters of that solution, 150 mils of that solution. So that cancels out. And that gives me my moles of lead 2 nitrate. Now that I have my moles of lead 2 nitrate, I can use my balanced equation. It was already provided in balance for us. And I see it takes 2 moles of KCl to react every 1 mole of lead 2 nitrate. No surprise, we need 2 chlorides for every 1 lead. This cancels out my moles of lead 2 nitrate. And now I've got moles of chloride. Or KCl, potassium chloride. The potassium is acting as a spectator. That's why I keep saying chloride. So I've got moles of potassium chloride now. I know I have a 0.15 molar solution. I need to know how many milliliters. I'm going to use that molarity as a conversion factor. And I'm going to say, okay, I know if I have a 0.15 molar solution, if I had an entire liter of that KCl solution, I would have 0.150 moles of KCl. Convert that to milliliters. 1,000 milliliters of that solution equals 1 liter of that solution. $350, put a decimal place here. If you just write 350, this has 2 sig figs. If you write 350 with a decimal, this has 3 sig figs. If you write 350 decimal 0, this has 4 sig figs. So this is acceptable, or you could write 3.50 times 10 to the second. Either one of those are acceptable, but you do need that decimal place there for sig figs. Milliliters of KCl. So it would take 350 mils of KCl to completely react and precipitate out all of these lead as lead 2 chloride. Sulfuric acid can be neutralized with potassium hydroxide. So this is acid-base neutralization reaction. If it requires 22.3 mils of a solution of KOH to completely react, okay, in this semester, we're dealing with completely reacting. Next semester, you can deal with anything, but this semester, we're going to completely react 42.7 mils of a 0.125 molar H2SO4 sulfuric acid solution. What is the concentration of the potassium hydroxide solution? Completely react means I have reached the equivalence point. Which means the moles of acid equal moles of base at that point. We have KOH, strong base, strong electrolyte, reacting with sulfuric acid, H2SO4, strong acid, strong electrolyte, producing, I'm still used to writing sodium, potassium, sulfate, K2SO4. Again, we're swapping partners. Here's what we're doing, which is soluble, and water, which is a liquid. Anytime you have an acid or a base, an acid that has 2 protons or a base that would have 2 hydroxides, so like calcium hydroxide, barium hydroxide. Pay attention to balancing this equation, please, because it's not 1-to-1. To balance, and I have 2 potassiums here too. I need to put a 2 here, a 2 here. Now my reaction is balanced. So it takes 2 moles of potassium hydroxide to completely neutralize that sulfuric acid. I'm trying to find concentration of the potassium hydroxide. I know concentration would be number of moles of KOH to number of liters of KOH solution. I know that I'm using a 0.125 molar sulfuric acid solution, and I was able to neutralize 42.7 milliliters, which is the same as 0.0427 liters. I also know it took 22.3 milliliters, which is the same as 0.0223 liters of my KOH solution. So I know 0.125 moles of sulfuric acid per liter And I'm going to multiply that by the volume of sulfuric acid used, 0.0427 liters. Because again, that gets me to my moles. I've got moles of sulfuric, but I need moles per liter of KOH. So I better get to my moles of KOH. There's 2 moles of KOH to every 1 mole of sulfuric. So 2 moles of potassium hydroxide are required to neutralize 1 mole of sulfuric acid. Now I've got moles of KOH. I've got my top half. All I need is my denominator here. So I've got the top half. I'm trying to find the denominator now, okay? What I'm going to do is I'm going to multiply this, or divide, however you want to look at it, 1 over my number of liters of solution, 0.0223 liters of KOH solution. This is going to give me 0.479 moles of KOH to 1 liter of solution, of KOH solution specifically, which we can write as 0.479 molar KOH. So if I had 42.7 milliliters of a 0.125 molar sulfuric acid solution, and it took 22.3 milliliters of KOH to completely react it, that means that my KOH had a concentration of 0.479 molar. Suppose a 2.5 gram sample of sodium chloride is required for a certain reaction. If the sodium chloride is available as 0.15 molar solution, so I need 0.25 and I've got a 0.15 molar solution, how many mils of the solution can be used or must be used to complete the reaction? So I want to know the mils of my sodium chloride solution I need. I know I need 2.5 grams of sodium chloride. Let's go ahead and convert that to moles. How many moles of sodium chloride is that? Sodium chloride has a molar mass of 58.44 grams. I know I have a 0.15 molar solution, which is the same as a conversion factor, so I know that 1 liter of that sodium chloride solution contains 0.150 moles of sodium chloride. So at this point, I've converted grams to moles. Now I'm converting moles to liters. I know 1,000 milliliters is equal to 1 liter. And I get 285 milliliters of NaCl. So if I needed 2.5 grams of sodium chloride to complete a reaction, but all I had available was a 0.15 molar solution, I would need to use 285 milliliters of that solution to be able to obtain the number of grams I needed. 17. Solid magnesium reacts with hydrochloric acid to form an aqueous solution of magnesium chloride and hydrogen gas. How many mils of 0.899 molar HCl are required to completely react with 1.92 grams of magnesium? So I've got magnesium plus HCl, giving me magnesium chloride and hydrogen gas. Remember, hydrogen is a diatomic. This is clearly not a balanced reaction. I need to put a 2 here. Now it is balanced. I want to know the number of milliliters of HCl. If I've got 1.92 grams of magnesium chloride and I've got a 0.899 molar solution here. So how many mils of HCl are required to completely react all of my magnesium? Trying to react 1.92 grams of magnesium. Convert that to moles. 1 mole of magnesium. Atomic weight is 24.31 grams. This is converted to moles of magnesium. Now, how many moles of HCl do I need? For every 1 mole of magnesium, it takes 2 moles of HCl to react 1 mole of magnesium. I've got moles of HCl. I've also got molarity here. So I know 1 liter of HCl solution will contain 0.899 moles of HCl. But I want milliliters because that's what I'm going to do in a lab. I know 1,000 mils of my HCl solution is equivalent to 1 liter of my HCl solution. This gives me 176 milliliters of my HCl solution. So the answer here would be B. What mass of solute is contained? So I don't know. Okay, so what mass of solute? Here I don't know what solute is. Contain 150 mils of a 1.25 molar sodium sulfate solution. Okay, so solute would be my sodium sulfate. Because sodium sulfate is going to be a solid. When I put this into a 1.25 molar solution, that means I'm dissolving in water, and it will change phase. Therefore, it's my solute. So I want to know how many grams I've got. Number of grams of Na2SO4 in 150 mils of a 1.25 molar solution. 1.25 molar means 1.25 moles of Na2SO4 to 1 liter of solution. $155 mils is the same as 0.155 liters. Why do I care? Because I need to convert this to liters to cancel out liters and get to moles of sodium sulfate. Now I'm in moles of sodium sulfate. Now I want to know how many grams because I want mass, so I've got moles. Now I just convert to grams. Add up the molar mass. Molar mass of sodium sulfate is 142.05 grams to 1 mole of sodium sulfate. 27.5 grams of sodium sulfate. So if I have 155 mils of a 1.25 molar sodium sulfate solution, that means it contains 27.5 grams of sodium sulfate. Which of the aqueous solutions below contains the greatest number of ions? The way to think about this is to think about how does this split up. So calcium chloride, CaCl2. I have a 0.1 molar solution. So I have 0.10 moles of CaCl2 per 1 liter of solution. I have 40 milliliters of that, which is 0.0400 liters of solution. I have 3 moles of ions to every 1 mole of calcium chloride. Avogadro's number is 6.022 times 10 to the 23rd ions to 1 mole of ions. For A, I get 7.23 times 10 to the 21st ions. And I know someone is going to ask me, do I have to convert all the way to ions here? Technically, no. You could convert just to the number of moles of ions, but I only recommend that if you understand the concept behind it really well. Otherwise, just please convert all the way to ions because I think it'll get you a better chance of getting on the right path and understanding the answer here. Okay, let's shrink this down drastically and put that here because we're going to 60 mils of a 0.25 molar acetic acid solution. So acetic acid, CH3COOH, is a weak acid. It will partially ionize. Let's go ahead and assume it's actually going to break into 2 ions, though. It will form H plus and CH3COO minus. Not all of them will break apart, but let's just assume it actually breaks apart. I have 0.2 molar, which is 0.2 moles of acetic acid in 1 liter of solution, times 60 mils, which is 0.0600 liters, 2 moles of ions. I know it won't actually break up into that many ions, but You'll learn more about that in second semester. 1 mole of acetic acid. And Avogadro's number, 6.022 times 10 to the 23rd ions per 1 mole of ions. And I didn't calculate this one out. So 0.2 times 0.06 times 2 times 6.022 times 10 to the 23rd. Gives me 1.44 times 10 to the 22nd ions. And let's continue this process. Is there a faster way to do it? Not really, because I have different concentrations and different volumes of each one. Ammonium phosphate, NH4, 3, PO4. 0.15 molar is 0.15 moles of ammonium phosphate. To 1 liter. I have 50 mils of it, so times 0.0500 liters. This is 4 ions, 3 ammonium ions and 1 phosphate ion. So 4 moles of ions to 1 mole of ammonium phosphate. And Avogadro's number. And I did calculate this out, but it's really shrunk down. This is I can't even read what I wrote. So I need to calculate this one. 0.15 times 0.05 times 4 times 6.022 times 10 to the 23rd. 1.80 or 1.81 with rounding. Let's see, 1.8 times 10 to the 22nd. Ions. I wasn't paying attention. There's 2 sig figs here. So this should technically be 1.4, and this should be 7.2. Shrink this down. I'm not going to write out all the work for the other two, but I will write out how we get there. So sodium nitrate, NaNO3, gives me 2 ions. And the answer for this one was 2.2 times 10 to the 22nd ions. And aluminum phosphate, Al2, SO4, 3, gives me 5 ions. And the answer here is too small to read, of course. That's what you get when you try to fit too much on a slide. Let's see, 0.2 times 0.05 times 5 times Avogadro's number. It's 3.0 times 10 to the 22nd ions. So which one has the most? These are my options. 7.2 times 10 to the 21. 1.4 times 10 to the 22. This clearly beats 7.2 times 10 to the 22. 1.8 times 10 to the 22. That beats 1.4 times 10 to the 22. 2.2 times 10 to the 22. That beats 1.8. And 3.0 times 10 to the 22. That beats 2.2. So E is my final answer. Which aqueous solution below contains the greatest number of ions? 50 mils of a 0.2 molar aluminum sulfate solution. Remember what aqueous means? It means in water. Number 20. What is the final concentration if 12 mils of a 12 molar HCl solution is diluted to 250 mils? Diluted, keyword. You can use M1V1. You don't have to use this equation. You're welcome to do it the long way. If you want to know what the long way is, ask me and I'll show you. But the long way is basically figuring out the number of moles you have and dividing it by the new volume you have. I like doing the dilution equation. M1, 12 molar. V1, 12.5 milliliters. M2, that's what we're trying to find. V2, 250 mils. We're solving for M2 here. M1, 12 molar. V1, 12.5 milliliters. V2, 250 milliliters. 0.600 molar HCl. So if I dissolved 12.5 mils of a 12 molar HCl solution to 250 total mils, my solution concentration would be 0.600 molar. What volume of a 1 molar barium hydroxide solution is required to completely neutralize, that means acid-base reaction, 25 mils of a 0.1 molar nitric acid solution? It does give us the balanced equation. Completely neutralized means I've reached the equivalence point. Which means stoichiometric moles of acid equal base. I say stoichiometric ratios because I've got 2 moles of acid for every 1 mole of base here. So I want to know the volume of barium hydroxide needed. So how many mils of barium hydroxide solution did it take to reach this point? I'm starting with a 0.125 molar solution, which was 0.125 moles of nitric acid in 1 liter of solution. Times 0.025 liters of nitric acid. That gets me moles of nitric. Now I convert to moles of barium hydroxide. I see there's 1 mole of barium hydroxide to every 2 moles of nitric acid. Now I'm in moles of barium hydroxide. I know I have a 0.1 molar solution, so I'm going to say 1 liter of barium hydroxide. I know 1 liter would contain 0.100 moles. So that's my way of canceling out moles of barium hydroxide and getting to liters, and then just convert to milliliters. I get an answer of 15.6 mils of barium hydroxide. So it would take 15.6 mils of a 0.1 molar barium hydroxide solution to completely neutralize 25 milliliters of a 0.1 molar nitric acid solution. What is the concentration of a solution of HCl that's prepared by diluting? So diluting is a dilution. 5 mils of 12 more HCl to 150 mils. So again, we've got your M1, V1. So what is the concentration? I started out with 12 molar. And I diluted 5 mils of that 12 molar to 150 mils. And I'm trying to find M2. Again, the reason I don't have to convert to liters here is because my mils are canceling out. So some students get confused by that, like why I'm not converting to liters. You can. It's just a point in the calculation that students, if you're going to make a mistake, it's just one more place to make a mistake. So I don't do it because I don't need to do it because they cancel it out. But you are welcome to if it makes you feel more comfortable. You do have to convert to liters in all other calculations with molarity, though. So 0.4 molar. If I take 5 mils of a 12 molar solution of HCl and dilute it down to 150 mils, that new solution has a concentration of 0.4 molar. What is the concentration of the solution described below? Well, let's see what's being described. We've got cobalt chloride dihydrate, COCl2 H2O, or 2H2O. This has a molar mass of 165.27 grams per mole. And I see I'm taking 10 grams of it, and I'm diluting it to a total solution of 500 mils. Grad cylinders are actually very specific. They're actually specific to your second decimal place, so it's like 500.00. And I want to know the concentration of this solution. It's concentration, number of moles of cobalt 2 chloride dihydrate divided by liters of solution. I have 10 grams of COCl2 2H2O. I need moles. 1 mole of COCl2 2H2O weighs 165.27 grams. So I've accomplished my first half. Now I just need to divide this by the liters of solution. I have 500 mils, which is a half a liter. So 1 divided by 0.50000 liters of solution. 0.121 molar COCl2. Why do I just write COCl2 here and not COCl2 H2O? Because this entire thing is dissolved in water. So I don't really care about the water at that point. I can tell you it's 0.121 molar COCl2. And if you wanted to calculate it through entirely, you would see there's 1 mole of COCl2 for every 1 mole of COCl2 2H2O. Just one more conversion. You could insert that in as well, and you get the same answer. Why am I using a dihydrate? In the real world, dihydrates dissolve easier in water. Or the hydrated salts dissolve easier in water. What mass of sodium chloride is required to prepare 300 mils, so mass of NaCl, 300 mils of a 0.1 molar solution? I want a number of grams of NaCl. And I've got a 0.1 molar solution, which is 0.1 moles of NaCl to 1 liter of NaCl solution. I need 300 total mils of solution, 0.3000 liters. I don't want to lose my sig figs. Had 4 sig figs there, so I'm keeping 4 sig figs. This cancels out my liters of solution and gives me moles. Now I can use the molar mass, 58.44 grams per mole, of NaCl to calculate the grams of NaCl needed. 1.75 grams of NaCl. So if I dissolve 1.75 grams of NaCl in 300 total mils, I would have a 0.1 molar solution. 25. How many liters of a 0.125 molar NaOH solution contains 0.255 moles of NaOH? So this time I want liters. Number of liters of NaOH. I'm told I want 0.225 moles of my NaOH solution. I know I have a 0.125 molar solution, so 1 liter of NaOH solution contains 0.125 moles total. .04 liters of NaOH solution. So if I wanted to have 0.255 moles, I would have to have 2.04 liters total of that solution to get that many moles. Determine the oxidizing agent and reducing agent in each reaction below. Remember, oxidation is loss, Reduction is gain. Oxidizing agents oxidize something else. Reduced themselves. Reducing agents reduce something else. Oxidized themselves. So let's look at each piece. H2S. The sulfur here is more electronegative. More electropositive elements are listed first. More electronegative elements are listed second. So sulfur will be -2. Overall, the hydrogen needs to be +2 to balance this out. So each hydrogen is +1. Nitrate, each oxygen is -2. Overall, -6. I have a negative charge here, so nitrogen must be +5 to get over to an overall -1 charge. 2 protons here, each one +1. Sulfur here, elemental, 0 oxidation state. Oxygen -2, so this nitrogen must be +2. Oxygen -2, 2 hydrogens, each one must be +1. So I see my sulfur going from -2 to 0. And my nitrogen is going from +5 to +2. So sulfur went from -2 to 0. Did that gain or lose electrons? That lost electrons, which means it was oxidized, which means sulfur is my reducing agent. It oxidized itself so something else could be reduced. Nitrogen went from +5 to +2, so it gained electrons, so it was reduced. So nitrogen is my, since nitrogen was reduced itself, it is an oxidizing agent. It was able to oxidize something else. Let's look at the next one. MnO2, oxygen, -2. Overall, this would be -4 because there's 2 of them, which means my manganese is +4. HBr, bromine, will be -1. It's more electronegative. Hydrogen, +1. MnBr2, each bromine will be -1. Overall, -2 charge. So manganese here will be +2. Br2, this is 0. Oxygen, -2, and each hydrogen, there's 2 of them, so each one will be +1. I see my manganese has changed. And in one case, bromine didn't, but in the other case, bromine did change. Let's see. So let's talk about manganese first. Manganese went from +4 to +2. Did that gain or lose electrons? It went down in its charge, so it gained electrons. Gaining of electrons is reduction, which means manganese was reduced, therefore it is an oxidizing agent. Bromine went from -1 to 0, so it lost electrons. It lost one electron specifically for one atom. Loss of electrons is oxidation. In order to be oxidized, that means bromine must be a reducing agent. It oxidized itself, so it was able to reduce something else. So bromine is your reducing agent. Okay, let's go ahead and practice some net ionic equations. Write the net ionic equation for the following reactions. Got 2 moles of sodium solid reacting with 2 moles of water liquid, producing 1 mole of H2 gas and 2 moles of NaOH. The only thing that's going to act as spectators are things that are not changing phase. So everything in this one, sodium, 2 Na solid. Water, 2 waters. Those don't split up. Solid and liquid is not going to split up. H2 gas stays intact. 2 moles of sodium ions and 2 moles of hydroxide ions. I have to write them as products. I don't have them on the other side. They're not spectators. So the net ionic is actually our total ionic as well. Let's look at the next one. We have HBr plus NH3 giving me Na4Br. Okay, this next one's actually kind of tricky. NH3 aqueous, ammonia aqueous. Ammonia is actually a gas. It's NH3 gas, and we bubble it through water. And when we do this, what we actually create is NH4OH. That's what's actually existing in solution. In this case, though, I'm going to react this ammonia that's being bubbled through with HBr, which is hydrobromic acid, a strong acid, and produce NH4Br. So I write this as aqueous, but it's actually gas bubbling through. So it's not behaving as an ion in solution. I am forming NH4 plus. So my net ionic equation here, bromine is truly a spectator because NH4Br splits up into NH4 plus and Br minus. NH4 plus here is being produced, so I can't get rid of that. I've got the NH3 and the H plus, but the bromine, HBr splits up into H plus and Br minus, so bromine truly is a spectator here. So ammonia, I'm writing it as aqueous. Some people get confused by that. It is technically ammonia gas that's bubbled through water to produce it. What about silver nitrate? 2 moles of silver nitrate reacting with copper solid to produce 2 moles of silver solid and 1 mole of copper nitrate. Well, I've got 2 silver solid here. Got a copper solid here. Got 2 silver plus and a copper 2 plus. Nitrate is my spectator ion. So this one has no spectators. This one, the spectator, is bromide ion. And this one, my spectator, is nitrate. And our last example. Bone was dissolved in hydrochloric acid, giving 50 milliliter solution containing calcium chloride. To precipitate the calcium ion from the resulting solution, an excess of potassium oxalate was added. The precipitation of calcium oxalate weighed 1.437 grams. What is the molarity of the calcium chloride in the solution? So I've got calcium chloride reacting with potassium carbonate And our last problem, at least for this chapter. Bone was dissolved in hydrochloric acid. This gave us 50 ml solution containing calcium chloride. To precipitate all of that calcium ion from the resulting solution, an excess of potassium oxalate was added. The precipitate of calcium oxalate weighed 1.437 grams. What is the molarity of the calcium chloride solution in the original solution? So I formed calcium chloride solution from dissolving the bone in HCl. I reacted this with potassium oxalate, and this forms calcium oxalate, which is insoluble, and KCl, which is aqueous. Potassium and chloride are acting as spectators here. I want to know the molarity of calcium chloride. I have 1.437 grams calcium chloride. That is 1.437 grams of calcium oxalate. CaC2O4. I'll get it right eventually. Convert that to moles of calcium oxalate. Add up the molar mass of calcium oxalate, and you find it to be 128.01 grams per mole. So now I've got moles of calcium oxalate, but I'm trying to find the molarity of calcium chloride. So I'm trying to find moles per liter here. I want to convert back to moles of calcium chloride. 1 mole of calcium chloride to 1 mole of calcium oxalate. I now have this, I just need liters of solution. I'm told I have a 50 ml total solution here. So I'm going to divide this by my total solution, 0.0500 liters of solution, and I find this to be 0.0224 molar calcium chloride. I hope this helps. This was a really long chapter, but I really hope these videos help.